Chapter 9.4, we're dilating in the coordinate plane. Dilating. Do you remember we had a little preview of this, I think, with your class? We said if you're dilating, you're doing one of two things. So here's our little guy. And you're either doing this, or you're taking him from this size and you're doing this, right? You're doing this. Woo. Now, how is that different than a translation? Emily? The sides are changing size, right? So a translation would be this. Would be just, woo, just moving him around. Now, is he changing size? No, he's just sliding around, okay? And then what was the other thing we did? A reflection? Oh, a reflection would be this. Watch this reflection. Everyone looking. Charlie, please look. Ready? Ta-da! Did you see that? And here, let's do it again. And here's a reflection. Ta-da! Okay. So that, is he changing size there? No, but with dilation, we now get to make a mega big Barney. Okay, so that's what we're doing today. And what did we say? Ooh, I like doing this. Okay, what did we say we're doing, mathematically speaking? When we were sliding, we were adding or subtracting, right? When we were reflecting, we were taking a negative, remember? We were taking a negative, boom, we took a negative value. But when we're dilating, what do you suppose we're doing? Hannah, good. Good, I heard somebody else too. Multiplication. So, dilation stretches or shrinks a figure. I'm going to shrink him way down. And we are multiplying by some scale factor K. Whoops, went too far. Okay, so let's put the rule down for dilating, since we know it's multiplication. And then we'll go do a really sophisticated question about this, okay? So to dilate a polygon, we're going to multiply the coordinates of each vertex by a scale factor. A way to show that is this way. Some point, let's say that P is a vertex, moves from xy to x times k and y times k. Okay? And then just to make sure we understand this, whoops, let's try this with a real number. A real point. If point P is at this location, 3, 2, and we have a scale factor of 2, please tell me where the image ends up. Apply this rule here, and then come back and check your work. I'm not. Okay, back to our math. And did you find the image of point P? And let's say together, point P prime is now at what point? What coordinates? 6 and 4. So you multiplied each of the 3 and 2. Here's the 3 and the 2 by 2, and you got 6, 4. Very good. So when we're dilating an entire figure, we do this for each vertex. And then we can see where the image is on the coordinate plane. Okay? So we now have a very involved question. So if you're watching this on video, you'll have to pause it and start taking this stuff down. The question is this. You have a triangle EFG, and here it is. It's given to you as ordered pairs. We're going to go ahead and plot this on a coordinate plane. Then we're going to do 3 things. We're going to dilate it using a scale factor of 2. And then we're going to find the side lengths of each triangle. And then we're also going to find the areas of each triangle. Okay? So pause and come back when you're ready to move forward here. Okay, so why don't we start by dilating by this scale factor of 2. So I'm going to jot that down here that the scale factor is 2, so I can get a little more room on the board here, and then we can work on the other stuff. But just the scale factor of 2, we're given this triangle. So Sterling, how do we find E prime? Can you tell me where E prime would be if E is given? job. So she's multiplying each of these by 2. And this, good job. So we should do this to all 3 points. So who has F prime? F prime, Riley.
2 times 2 is 4, and 4 times 2.
Good. And the last one, G prime, right?
-4 and 2.
And 2. Good. So who has plotted these already? Good for you. So I'm going to do it quick because so many of you have done it. -4, 8. That's our E prime. 4, 8. That's our F prime. And -4, 2 is G prime. So when we connect these segments, or these points, we have what appears to be a triangle that looks the same shape but is a bigger size. Do you see that? So when we dilate with a number that's greater than 1 like this, that's 2, we've made a triangle that is larger. We've actually enlarged it is the word, right? So now we're going to answer the other 2 questions. Find the side lengths and area. Okay? So I'll use block for the first triangle. Side lengths. Can somebody give me the side lengths? If we just look at this name of the triangle, could you give me the side lengths? Wesley? Or I mean, give me the names of the sides so we have them down. Good. Okay? And then I guess we can come over here and say we have those after they've been dilated. So we can just add the prime, right? F, G, and GE. Okay? So when we are actually giving the length, we don't write the segment bar over the top. We don't write that. Okay? Because that means segment EF, and this means the length of the segment. So it's one of those finer details, right? Who can find the length of EF? Here it is, EF. I'm sure you all can. Chris, can you see it? What is it? One, 2, 3, 4. Okay. Let's go to GE. Going from G to E is straight up and down. It's a vertical line, right? Vertical segment. And Faith, how far is that? How long is it? One more time?
3.
Good job. 3. 1, 2, 3. 3 units. Okay. FG is tricky. Look at it. FG is like a diagonal. So, what type of a triangle is EFG? It's a right triangle. So what can we use to find this diagonal? Hannah? Excellent. Very good. A squared plus B squared equals C squared. Now, the other thing you might remember, if you remember, is I told you the most common right triangle in the whole universe is the which triangle? Do you remember? Who remembers? Lauren? The 3, 4, 5. And 5 would be the longest side, which is the missing side here. So when we plug these numbers 3 and 4 in for A and B, we do get a C value of 5. So we found it. We just found it because we know the 3, 4, 5. If you don't remember that, you could find it by plugging these numbers in. Okay? Let's go ahead and find the prime. How about E to F? E prime to F prime. Dylan. Do you have it on your page? Alana. 8. Good. If you count it, it's 8. 1, 2, 3, 4, 5, 6, 7, 8, which is why you have it on your own paper. Okay? And then going from, let's do the easier side, G prime to E prime, the straight up and down side. And how long is that, Nick? You're right, it's 6. Okay. And then we need this missing side, G. Oh, I put that in the wrong spot, didn't I? I skipped that one, so this goes here. And now we need F, G, the prime. And Wesley, did you find it? How did you find it? Very good. Look at what he sees. He sees a pattern. He says 3, the side 3 became 6. The side 4 became 8. So the side 5 might become 10 because it's a scale factor of 2 in this case. So it doubled it. Very good. Now we need to find the area. Wow, we have a lot to do. Okay, so let's just jot down the formula for the area of triangles. Ready? A equals Good. And what must be true about base and height? Lauren? Right angles. So be careful of the base and height you choose. With our the little black triangle here, we're going to use the sides that are perpendicular, right? So who can fill in the formula? Can you fill it in, Lauren?
A equals 3 times 4 over 2.
So what does A equal?
8 equals 6.
6 units squared. Good. And go ahead and finish the large triangle and come and check your...
I multiplied 8 and 6.
8 times 6 over 2. So you got 24. Very good. Good job. Those are the sides that were perpendicular. Excellent. Okay. We need to talk about what happens if you shrink a figure. So if we go from a larger Barney to a smaller, we are multiplying by a fraction between 0 and 1. Like 1/2, right? Which feels like division. So that will shrink an image. Okay? So you probably will have an opportunity to shrink something as well as enlarge something in your assignment. Okay, we're going to find a scale factor. Find the actual factor something has been changed by. Now, the book gives you a little bit more complicated kind of ratio, but I'm going to tell you this. If we have, let's say, give me a number, any number.
8.
Dylan. No, something bigger than 1. Sterling. 3. Okay, Sterling says 3. If I have 3 and it becomes 18, what is the factor that has caused this to be enlarged? Sterling.
6.
Very good, you found it.
Yes.
So the scale factor would be 6. Do you see? Very good. Okay, so let's put this in words in the form of a rule. If you have an original, in our example, the original was 3. And it becomes something new. The something new was 18, right? Then your scale factor must have been 6. Okay? Now watch what can happen. The scale factor is K, right? Let's say the original is P. P is the original. And it becomes P prime, right? It becomes, P prime is not P. That's something different, right? If I wanted to get K all by itself, what would I have to do? Divide by P. So we would divide both sides by P, and we have K equals the new, see this? The new, the image over the old, doesn't it? And your book writes that out in big long words, okay? So if you want to know the scale factor, you can find it by dividing the new number by the old number. So let's see how this works with a segment. We have a segment AB. And all you really need to do is look at one point to know what happened, right? So I want to know how we got from A to B. So all I have to do is look at, let's say, my X value. I went from 1, and then I became 1.5. What did I multiply myself by to get to 1.5? 1.5. So the scale factor here is 1.5. Okay? It's that simple. The other way to look at that is to say the new image is 1.5 and divide that by 1, and what do you get? 1.5. The whole weekend.